Today we talk about the extra dimensions, and the fundamental question is how many spatial dimensions are there in the universe. This is really as fundamental as asking, is supersymmetry realized? So the motivation to consider more spatial dimensions in addition to the usual 3 dimensions in which we experience every day come from a number of facts. First of all, they are essential for string theory. Remember also that supersymmetry was essential for string theory, which is the best framework we know of to quantize gravity. Also, the general relativity, which deals with describes the space-time and gravity, is easily generalized to the bigger than 4 space-time. In fact, immediately after the theory was formulated, there was a GR in 5D construction by Kaluza, 1921. And finally, the motivation that we will be primarily interested in from the particle physics point of view is that extra dimension can actually help to resolve some long-standing puzzles in particle physics. For example, the hierarchy problem and the flavor puzzle. And the goal of today's lecture would be to demonstrate these things. Okay, so the literature is listed here. There are 2 very nice lecture notes from Tassi that discuss this subject, and there's also another lecture notes which is called Beyond the Standard Model. Okay. So clearly, this additional extra dimension or dimensions should be different from the usual, three spatial dimensions. We have tested the law of gravity. It's up to some length scales. The potential, gravitational potential goes as 1 over r. And if there was another spatial dimension, this law would certainly change by order 1. I just want to remind you of a basic thing, of a basic law in electrodynamics, for instance. So if you have a charge, and then you're looking at the flux through a closed sphere, then the flux is proportional to the charge. So the electric field, the flux is electric field times the area. And so if you have more dimensions, then the area is increased, right? So the electric field is decreased. So clearly these laws change in more dimensions. So in particular, the modification. So now these dimensions have to have some special properties. For example, if you introduce a finite size of this dimension, extra dimension L, and also there is this factor alpha, which depends on the geometry of the dimension. The gravitational potential is changed by this factor over here. So you see this Yukawa type, sort of Yukawa potential, which is due to exchange of some massive particle, which has the mass of this particle would be the inverse length of this size, the inverse size of the extra dimension. You will see later on it has to do with these Kaluza-Klain gravitons. So the fact that we test gravity puts a constraint on L as well as alpha. These things should be small. So if this is small, then at large distances r where we measure gravity, this term simply vanishes. The exponential dies off very fast. So there are several options about the way of aiding the tests of gravity. So first of all, extra dimension can be curled up. So it can be, for example, we can have the the extra dimension to be a circle. So we have it compactified on a circle, so a compact extra dimension. So you can imagine this cylinder where this infinite direction is basically would be our 3 spatial dimensions, which are infinite and flat. And then there would be this additional extra dimension, which is compactified on a circle. So this is it is curled up and therefore small. Another option is that extra dimension exists on a finite on interval. Okay. This can be, so we are considering only the slice of the space, and this can be achieved by introduction of the so-called branes, which I will discuss later on in more details. But at the moment, you can think of branes to be lower dimensional surfaces. So these are some lower dimensional spaces in a big space, and they actually provide the boundaries of this big space. Okay, so the extra dimension is perpendicular to these branes, and branes provide boundaries, and there is no space here, for example. So the space is only in between the branes, this additional space. So we will call this space the bulk, okay? This higher dimensional space, and the brane will be just a lower dimensional surface, which is the boundary of this space. And this interval L can be small, much smaller than something to satisfy gravity tests. And the final option, which I will not discuss too much in this lecture, will be the fact that L can be even infinite, but then there is something funny going on with the geometry. And in particular, if you have a warped geometry, then you can evade these tests of the gravitational law, even though having infinite extra dimension L. All right, so that's how the extra dimension can look like in order to escape the tests of gravity. So it can be either curled up, or it can be on the interval, or it can have some funny geometry. The first big topic to this, the first big implication of extra dimensions is something which is called Kaluza-Klain decomposition. I will show you this KK decomposition on an explicit example. So I will take one extra dimension. I will add one extra dimension, which is compactified on a circle of radius r. So I will have a circle of radius r, and r is small. I will work with a flat space, so the metric will have the usual. So I will work on a flat space, and the metric will have the usual flat space form. So there will be these m and n indices, which run from over the usual 4-dimensional 0, 1, 2, 3, and there will be additional coordinate, which is this fifth coordinate, and the corresponding term in the flat metric is this one. So x mu are the coordinates, space-time coordinates in our 4D space, and then there is this additional extra dimension with the coordinate y, and the geometry of the space is flat. So let's take a real scalar field in 5D. So the field will now be a function of 5D coordinates, x and y. And this will be the kinetic term for the field. Okay. And now the action is given by the integral over the entire space, both the x and the y. And the integral over y is on a compact interval because y lives on an interval. So we have the action, and we can, for example, calculate the equation of motion in the bulk, meaning in this entire space, 5D space. And this is just a 5D Klein-Gordon equation. So we have a free scalar field. It has a Klein-Gordon equation in 5D. And this is how it looks. So this is the derivative with respect to all coordinates, and it separates, factorizes basically into the 4D part and the derivative over y. So we have this factorizable geometry. Plus, we are on a circle, right, or finite intervals. There's a periodic boundary condition. These are special features. So whenever we have a function on an interval, it's smart to represent it by a Fourier series. This is a very general representation of a function, phi of x and y. It will be a Fourier series. There will be these Fourier modes, which depend on y. For every n, we have a different frequency. And then there is these coefficients, Fourier coefficients, which, however, are the function of x only, right? So we are doing the decomposition in y. Expansion, sorry, the series in y. Okay, so these phi of n are functions of x only. So these are fields in 4 dimensions, the usual 4-dimension fields. And there is an infinite tower of them. N goes from minus infinity to plus infinity. Okay. Since we started with a real scalar field in 5 dimensions, there is this reality condition, namely that minus n are related to n by the charge conjugate. This relation between Fourier modes provides that phi of x and y is a real field. So now let's take this general form representation of the field in terms of the Fourier series and plug it in the equation of motion. So we are acting with a Klein-Gordon operator in 5D on this field phi. Okay, and you can do this, and then what you will get is this form. So there will be this, so we will have infinite sum, and there will be these Fourier modes. And then we will have these coefficients. Since the Fourier modes are orthogonal, right? There is the orthogonality of these modes. Then in order to this to be zero, this Klein-Gordon equation in the 5D, it means that each individual coefficient has to be zero. So this means that each of these phi n fields satisfies equation, the Klein-Gordon 4D Klein-Gordon equation. And in particular, you can see that the mass of the field, right? Remember that the Klein-Gordon equation is delta square minus m square phi equals 0. The mass of the field depends on n. There will be this n over mass will be basically of this Fourier mode will be n over r. So we will have a tower of states in 4D with the mass n over r. Notice that I can clamp together phi n and phi of minus n. These are 2 real degrees of freedom to have a complex massive mode, because these 2 guys have the same mass. So I make a complex massive mode by taking these 2 together. Okay, so the 4-dimensional action, after we integrate over y, looks like this. We have one real scalar field, which is massless, phi 0. And then we have a tower of complex scalar fields, which are massive, which is this thing here in the bracket. This is called the Kaluza-Klain tower of states. they are separated by 1 over r. So the first excitation has the mass of inverse r. The mass of the KK mode is the inverse r. Okay, and then there is a tau of these things. If there are more extra dimensions, or if there is a bulk mass term means, so over here, if there was a term over here, minus m0 square over 2 phi square, the mass term for the 5D field, then it would simply, the formula would be simply like this, m0 square plus, for each dimension, there will be this, these modes. Okay. Right, so this, that. Okay. This example was for a very, very specific, right? We had a flat space, which is compactified on a circle. However, there is a general lesson to take from this example, which holds even in curved spaces, or with, for example, warped geometry that we will discuss later on. That we have these boundary conditions, which means that in this additional dimension, we are doing a quantization. We're quantizing the momenta. And in 4D, we basically, this manifests as a tau of resonances. So the details of the spectrum, for example, the spacing between will depend on the geometry. So if you have these, when you have these boundary conditions, then you will have the Kaluza-Klain tau in 4D. So not that is somehow, I mean, just from looking at it from far, so these theories are producing a bunch of resonances. And this really looks like some strongly interacting sector, like, for example, QCD, that there are many resonances which are generated. Indeed, there will be a connection between these kind of theories with QCD-like theories through the duality by the end of the class. Any questions so far? Okay. So let's talk about the gauge fields in 5D. So let's take some U1 gauge boson, which is a vector. This is a vector field. And M runs from 0 to 0, 1, 2, 3, 5. So first of all, this is a vector under 5D Lorentz group. And so the 5D Lorentz group is SO14. So SO13, the usual 4D Lorentz group, is a subgroup of this one. So therefore, we have to decompose the vector representation of 5D Lorentz group under the 4D subgroup. In this decomposition, we have 4D vector field and 1D scalar field. That representation is reducible and introduces to a 4D vector field and 1D scalar field. Okay. So in 4D, we have a vector field and a scalar field. Now let's start with the action. So the action is, of course, the space integral over the kinetic term, where F mu nu is the field strength tensor, defined by this relation. In particular, F mu nu is antisymmetric in Fmn is antisymmetric in M and N indices. Now we can expand this kinetic term in terms of 4D indices mu nu and the fifth component. And this is the form which follows because of the antisymmetricity. And note that you will have A5, A mu mixing. So there will be scalar vector mixing, okay? Now we should go to 4 dimensions, so integrate over the extra dimension by first writing the 5D vector field as a Fourier series and plugging in. So here I am doing the calculation. So I'm basically integrating over the extra dimension from 0 to 2 pi r. And here there is a double sum over the modes of one and the other field. And I'm doing it for this mixed scalar vector term. So at this point, I should use the orthogonality of the Fourier modes, namely this relation that the integral is proportional to the Kronecker delta, which will reduce double sum to a single sum. And in the single sum, I will have this minus n and n, okay, modes.
Admir, sorry, may I just ask one question?
Yes, please, go ahead.
So we use here the orthogonality relation, but aren't also the fields here, I mean the gauge field, isn't it also a function of y, or?
No, so these are these coefficients, Fourier modes.
Ah, okay, sorry.
So they are a, m, n of x, okay?
Okay, thanks.
So these when they have a superscript n, they are the function of x. They are 4D fields. Okay, so now at this point we can recognize for each n that we are now in 4D. For each we integrated over the extra dimension, we have gauge Goldstone mixing. So it's remember you have the usual term of the derivative pi on w. So this is the gauge Goldstone mixing, scalar vector mixing. And we can use the gauge transformation to gauge away scalars. In particular, in the axial gauge, remember the gauge transformation goes as you are modifying the gauge field by the derivative of a scalar field. So if you choose this kind of transformation, and then you plug it in over here, perhaps you can do this math offline. Then you will remove the entire tower of scalar fields where n is not equal to 0. You will still remain with one real massless mode, but the rest will be eaten up, and the vector field will become massive. Okay. So finally, in 4D, this is the Lagrangian density in 4D, the Lagrangian in 4D. It will have one massless scalar and one massless vector. And then there will be a tower of massive vectors. So the tower of massless vectors ate the tower of scalars. And now we are only left with the tower of massive complex vectors with the mass n over r. Okay? So you will have massive vector, Kaluza-Klain modes of the massive vectors. And so on. Perhaps you can do yourself the spin 2 graviton example. I will only state the result here. So in 5D, you would introduce a symmetric tensor field with two indices, m and n, and it's a symmetric tensor, the exchange of m and n. First, you will decompose it under 4D, and you will realize that you have the graviton field, the usual 4D graviton, and then you will have one vector field and one scalar field. This is in 5D. So this is 5D decomposition to 4D. So in the spectrum, we have one massless graviton, vector, and scalar. In particular, this scalar will be interesting. It will play a role of, later on in RS of the radion field. Except for these massless modes, graviton is the usual thing which imitates the gravity. There will be a tower of KK modes of massive gravitons. So the KK modes of gravitons are spin 2 particles. They are massive, and they have 5 degrees of freedom. Remember, the spin J has 2J plus 1 degrees of freedom. So there will be 5 degrees of freedom. And these 5 degrees of freedom come from the 2 degrees of freedom for massless graviton, 2 degrees of freedom for massless vector, and 1 degree of freedom from the scalar. So graviton will eat up the towers of vectors and scalars. These spin 2 Kaluza-Klain modes are the most generic predictions of the extra dimensions, and they are extensively looked for at the LHC. Spin 2 KK gravitons, one of the benchmarks in BSM searches at the LHC. All right, so that was the decomposition of the fields from 5D to 4D. Now there is also the couplings. One also has to manage the couplings of the 5D theory to 4D. Sorry. Matching the couplings is the next subject. Remember that the mass dimension of the coupling depends on the space-time, on number of the space-time dimensions. And this is familiar from renormalization, where you, for example, count the superficial degree of divergence in renormalization. That this very much depends on how many spatial dimensions you have in your theory. Let's do this counting for the 5D. So the action has no dimension, right? Then the Lagrange density has dimension 5. Okay, the Lagrange density, because it's integrated over d5x, d to the d5x, yes. And from the kinetic term, you can figure out the dimensions for different fields. So the scalar and vector are 3/2. Remember, in 4 dimensions, they were 1, okay? And the fermion field is 2. Actually, from the Fourier series, you can see that these coefficients have this. They have this square root of r, which gives the proper normalization of the Fourier modes. And square root of r carries 1/2 dimension, right? And therefore, a 5D field, the dimension of the 5D field is the dimension of the 4D field plus 1/2. Okay, so the fields in 5D have, on top of their ordinary 4D canonical dimension, you add 1/2 for a scalar, vector, and fermion. Okay. So, what about the gauge coupling? Remember that this is term in the Lagrangian. Lagrangian has dimension 5, and therefore we can just simply, sum up the dimensions, and we will figure out that the dimension of the coupling, of the gauge coupling, is -1/2. Remember, in 4D, gauge coupling had no dimension, was dimensionless. Okay, in 5D, gauge coupling has a dimension of -1/2. So it has a negative mass dimension, so it belongs to the class of irrelevant operators. This is just an effective theory. So there is a cutoff of this theory. For example, the Planck scale, where we need to have the quantum gravity. So in particular, we expect this G5 to be of the order of the square root of the cutoff, let's say the Planck mass, or the cutoff of 5D theory. It's a dimension-full coupling. Okay? This is very important. So the matching is done by performing the integral over the extra dimension. And then we derive simply this relation. Or if you do it in great generality, where you have an arbitrary number of extra dimensions, then you can conclude the following: that the four-dimensional gauge coupling squared is equal to approximately the gauge coupling squared in 4 plus d, where d is the number of extra dimensions, over the volume. So this is very important. Over the volume of the extra dimensions, if there is one over the size of this extra dimension. So what does this mean? So if, for example, electromagnetism propagates in the extra dimension, it gets diluted. The force gets diluted. So again, it's very important to remember, if you have a gauge coupling in extra dimension, G4 plus D, then when you do match to the four-dimensional theory, then the gauge coupling in 4D will be diluted by the volume factor, by the size of the extra dimension. For example, if you have a QED in the bulk of a flat 5D, then the structure constant would be 4 pi over M5 times cell. M5 would be the cutoff and of the theory, and L would be the size of the extra dimension. So if you have a large extra dimension, you would have a tiny gauge force. Okay, questions about this? Is this clear? So it just comes from the integrating over the extra. So in this integral, you get the volume.
It's clear to me. All
right. How about gravity in flat extra dimension? So let's start with the Einstein-Hilbert action, simply classical general relativity. So this is the Einstein-Hilbert action in 5 dimensions, from which the equation of motion of this will be Einstein's field equations for the metric. So the action is the integral over the Ricci scalar, and there is the volume factor, is the square root of minus determinant of the metric, and this general relativity, and then there is the integral over d5x. To match the dimensions, there should be a scale over here, the cutoff scale. We know that GR is just an effective theory. Okay, it has a cutoff M5. In 4D, this is the Planck. In 4D, this is the Planck scale, and M Planck is simply the we measure the G Newton, the Newton constant, and M Planck. So Newton constant is simply 1 over M Planck squared. So it is just the measured strength of the measured strength of the gravitational force in 4D. Is this coefficient M Planck in the 4-dimensional action? So here you should remember from GR that the dimension of the Ricci scalar is 2. The dimension of the Ricci scalar is 2. So Ricci scalar is related to the derivative of the connections, and this is the derivative of the metric, and metric has no dimension. Okay, so now we should do the matching. So the matching is done here. So we are integrating over the extra dimension and matching on the 4D action, and then we get this. We get the m Planck squared is m5 cube times L. So notice that so m5 is really the cutoff of the theory. The theory is formulated in 5D, and m5 is the cutoff of the theory. It is this thing here, cutoff. M Planck is the measured scale of 4D gravity. It's the G Newton to the -1/2. And there is this L. In general, L is the size of the extra dimension. So the general formula, if you have more extra dimensions, would be through this volume VD. So what does this mean? It means that also gravity gets weaker by propagating in the extra dimension. There is this volume factor, VD. So you can look at this from this perspective. If we have extra dimensions, okay, then the cutoff of the theory is much lower from what we expected. So if we in particular have a large volume, then M5 is smaller to match the observed gravity coupling. MP is simply related to the coupling that we observed of the gravity. And this can be interesting in the context of the Higgs hierarchy problem. So perhaps gravity is propagating also in the large extra-dimensional volume, and therefore the effective M Planck looks big, even though the fundamental scale is not far away from the electroweak scale. Okay. The fundamental scale, the cutoff of the standard model, is not far away, but there is a large volume which then blows up this effective Planck scale that we see from measuring the Newton constant. So we solve the hierarchy problem by saying that the cutoff is not far away. Okay. However, this really doesn't work very well if also other fields propagate in the extra dimension. For example, if QED also propagates in the extra dimension together with the gravity, then you have two equations, and you can solve for M5 and L for the size of for the cutoff and the size of the extra dimension in terms of the coupling for QED and coupling for gravity. And therefore, you can see that the size of the extra dimension is of the order of around M Planck, inverse M Planck, which is not very interesting. The effective scale M5 is also around M Planck, which is also not very interesting for the hierarchy problem, nor for the experiment. Okay. There was a very revolutionary work in 1998 by Arkani Hamed, Dimopoulos, Diwali, which takes this idea that we have extra dimensions, large extra dimensions, which dilute the gravity. So actually, the effective cutoff of the theory is much lower. The cutoff of the theory is much lower, and there is gravity propagates to the extra dimension. So the effective coupling of gravity, effective Planck scale, is the product of the cutoff times the volume. Okay. But we don't want to put the other fields, standard model fields, also in the extra dimension, because then also, for example, QED would get diluted. So to keep what we want for gravity, but not to dilute the electromagnetic and other gauge forces, we put the standard model fields on the brane. Okay. So branes are these hypersurfaces in the higher dimensional space, which have localized energy momentum in such a way they can trap the fields. So quantum fields can really live on a brane. So these objects are studied in string theory, and these are like solitonic objects which form lower dimensional space. Okay, so all you should remember is that these are like hypersurfaces which trap fields on them. These are some configurations which form lower dimensional space, and you can put fields on them. So the idea of Arkani-Hamed-Dimopoulos-Duval is to have large extra dimension through which gravity propagates, but you have branes, and standard model fields live on the brane. Okay. So standard model fields live on a brane, and only gravity propagates through the bulk. So this is the picture. So for example, imagine you have a cylinder, which is this extra dimension, and just one slice of is the brane, okay, one brane. And on this brane, you have usual standard model stuff, let's say like QED interactions, while the gravity propagates through the entire thing. Okay. So the cutoff of the theory, they put to a TeV scale. Okay. And we expect to see quantum gravity at the TeV scale. Okay, the completion of the gravity. We don't have a hierarchy problem because the Higgs mass is close to the cutoff. Okay. It's only gravity that gets diluted, and the effective M Planck is huge. So remember, M Planck will be the cutoff to this power, TeV L. Okay. So now if this is 10 to 16, then the Planck mass can really be matched to what is observed, 10 to 19 GeV. D is the number of space-time dimensions. Now, you can see if D is 1, L has to be very big, like, I don't know, extra dimension up to the planet Jupiter, which is excluded by tests of gravity. Even L equal 2 is excluded by tests of gravity. And now we are testing sub-millimeter scales, okay? So large dimensions of the order of sub-millimeter and at least 3 additional extra dimensions. In fact, ADD model doesn't really completely solve the hierarchy problem. It simply transfers the hierarchy between the Higgs mass and the apparent Planck scale, which comes from the measurement of the Newton constant, it translates this hierarchy into the hierarchy between large extra dimension and inverse TeV. So now TeV is the cutoff, okay? And the inverse TeV is some fundamental length scale. Then why is large extra dimensions? Why is this, for example, sub-millimeter, etc.? Why is it so much bigger than inverse TeV? And this is the hierarchy problem. There are some attempts to address this problem. But it seems it is not very easy, not very straightforward. Anyways, there are really exotic predictions for the Large Hadron Collider. So imagine you have the completion of gravity at the TeV scale. So for example, you can produce black holes at the LHC. In proton-proton collisions, you can produce a black hole, which will then decay by Hawking radiation to the standard model degrees of freedom. So this is modeled by some semi-classical approximations, since we don't have a full theory of quantum gravity. And in particular, ATLAS and CMS are looking for microscopic black holes. This is one of the ATLAS analyses. They are looking in the distribution of the sum of the transverse momenta of particles in the event. And here you can see these benchmarks, which tell you that for example, 6 or 7 TeV mass black hole would predict increase of events at the very high energetic tails of this distribution. which is not observed at the moment. So experiments are already setting very strong limits, 8 TeV mass of the black hole. So this is really like a bomb in the detector. It's a very exotic and interesting signature. Okay, do you have any questions about ADD model and how it solves the hierarchy problem? Or any other question?
I didn't quite get how we get the TeV scale.
Oh, that's an assumption.
Ah, okay.
So they just say that the fundamental scale is a TeV scale.
Okay, and if it
and this assumption is from the hierarchy problem. So we know that the Higgs is quadratically sensitive to, the Higgs mass is quadratically sensitive to the new scale, new physics scale. And we know that we need to quantize gravity, okay? We need the quantum theory of gravity. Okay, so maybe quantum gravity is at the TeV scale, which is not far away from the electroweak scale, in such a way that corrections to the, well, when I say TeV, you can, some little hierarchy, for example, you can push it to several TeV, or I'm talking about the orders of magnitude. The loop corrections to the Higgs mass are not very big. Okay, that is the motivation why they just say it's at the TeV scale.
Okay, I understand. Thanks.
And so quantum gravity, the cutoff of the theory is at the TeV scale, very close, and gravity is weak. Newton force is Newton constant is very small because there is this dilution by the volume of the extra dimension. Gravity propagates through the extra dimension, while other forces are trapped on the brane. Standard model fields, which are matter and forces, are trapped on the brane. Okay. Any other questions? All right. I will stop here, and then in 2:15, we will start with the other class of extra dimensional models, the warped extra dimension. All right, let's start with the second class. So far we talked about flat extra dimensions. In particular, large extra dimensional model, or ADD model, was one example of those. So the geometry of the space was flat. Okay. Now we will talk about other classes of these theories, where the space-time is highly curved. Okay, the metric is highly curved. So the prime example of these models, where the bulk is highly curved, is the Randall-Sundrum model, RS. The Randall-Sundrum model, and the reference goes to 99. In this paper, in this first version of the RS model, the gravity is very similar to before. The gravity propagates in the bulk, and the standard model is on the brane. Okay. So the extra dimension is warped, and its metric is not non-factorizable. So okay. So how did they achieve this configuration? So they studied basically Einstein's GR equations. So they put the following setup. They assume that there is a 5D bulk, okay, 5D space, which is bounded by 4D branes. So there are two branes that provide the boundary of the higher dimensional space of the bulk. You should think of this picture. This is their setup, okay? Now they require that these branes, that they are infinite and flat, okay? And with this, they solve the Einstein GR equation. They get the metric of this space. The metric which comes out is the ADS5 metric, anti-de Sitter in 5. They get anti-de Sitter space. So the metric which comes out has these two interesting properties. First, there is this warp factor, A of Z. That's called the warp factor. which multiplies this term, and it's a function of z, where z is the coordinate in the extra dimension. So a of z is r divided by z. R is the curvature, the inverse R is the curvature of the space. It is also, as you will see later on, it will be the UV cutoff, inverse, the curvature of the UV cutoff of this theory. That's important fact which comes out, assuming this setup, assuming that we have this infinite and flat four-dimensional branes, the solution to the Einstein's equation for the metric of the space. So you get enter de Sitter space with this warp factor. And in this part here, you can see this flatness in 4D. So eta mu nu is just the flat metric. So for each slice, for each z, you have in 4D slice, you have flat space. And therefore you can realize Poincare invariance. Okay. So that is how the space looks like. So there is a bulk, and then there are these two branes. But the important question is, like, what gravity does to this setup. So does it collapse these branes, or maybe they run away from each other? And there should be a way to stabilize these branes, the distance between the branes, in order for this setup to make sense. So this is done by another seminal paper, which goes by the name of Goldberger-Wise mechanism, a very efficient and elegant mechanism to stabilize the branes. So to have this configuration of space with this metric, and to have stable distance between branes. Maybe I could say something more about the Goldberger-Wise mechanism, the way how it works. So there is a scalar field in the bulk, the additional scalar field in the bulk. You can write the potential of it for these localized to these branes. This scalar field with such a potential will give a potential for the radion. Radion was this massless scalar graviton component, which we introduced when we did the KK decomposition of the spin to graviton. So the radion will receive a potential, and radion is the part of the metric, G mu nu metric, so the scalar massless mode, which is basically related to this fifth dimension. Okay, the wave of the radion is the size of the fifth dimension. Okay, so the wave of the radion is this r prime, the size of the fifth dimension. And so now this additional scalar, which with such potential configurations on the two branes, will create a potential for the radion field. There will be two competing contributions. For example, the kinetic term of this new scalar field will give a contribution to the radion potential, which push in one direction, and the mass term will be pushing in the other direction. So the radion field will have such potential to develop a wave. Then you can get to the formula where you have the ratio of r over r prime will be some parameter, some order 1 parameter, and there will be exponent. Okay, some minus order 1 parameter. This will what will come out from when you minimize this potential. So then you can see that if you have these order 1 numbers to be 10, 16, okay, and then you can get very hierarchical ratio of r over r prime. Also, the addition of this addition, so there is a back reaction when you add this field, the scalar Goldberger-Wise field, then you have to see whether you go through the Einstein equation to see if your metric changed, but you can still see that you have the anti-de Sitter metric. Okay. So now, how does this help to solve the Higgs hierarchy problem? This kind of geometry of space. So again, we have two branes. the brane with the coordinate z equal r is the UV ultraviolet brane, and in particular it is the Planck brane. We call it the Planck brane, and you can show by doing a matching calculation of the Hilbert-Einstein action of in 5D to 4D. You can show that M Planck is basically inverse R. R is the smallest length scale, and therefore the inverse R is the cutoff. Okay, and the gravity is sort of localized on that brane. So you can show, I will not do it here, that the cutoff is M Planck, and R is the M Planck inverse. And then there is another brane located at Z equal R prime. And R prime, in here we take to be TV. And this is the weak brane. R prime is TeV inverse. So these two branes are UV brane and infrared brane. Okay, so gravity propagates through the space, but is localized on the UV brane. And what about the Higgs field? So the idea of Randall-Sundrum is to say that the following: the Higgs field is localized at infrared brane. That's the idea. So the Higgs field is localized at R prime, the infrared brane. The Higgs field is localized here. Remember, branes are these configurations, solitonic objects that can trap the fields. Okay, so let me try to derive how is this helpful. So now the Higgs field will talk to the 4D component of the metric evaluated at Z equal R prime. In particular, this is how this 4D component looks like, G hat mu nu. So it will have this warp factor R over R prime squared and times the flat metric. We can calculate the volume factor by doing the determinant, and this is this factor, R over R prime to the power of 4. From GR, you would remember that when you rise the indices, then the metric with rise the indices is the inverse. So it's basically R prime over R instead of R over R prime. Okay. Okay, so this is the action. We are localizing Higgs on the infrared brane. So we can write this action first like the integral over 5-dimensional space. And we can integrate over the 5th dimension, inserting a delta function, a localization on the delta function Z minus R prime. And when you integrate over Y, this is what you get. This is what you start with, okay? So now we can plug in the volume factor, and we can plug in the metric. So it will be R over R prime to the power of 4 and R prime over R squared. And now we have these contractions are the flat space with eta mu nu. Okay? So now we have to canonically normalize the Higgs. We will write the Higgs field as this ratio R prime over R times the Higgs. Okay? I hope you're following. So now when I plug into this action, this formula, I will get rid of R's in the kinetic term. So I will have just the usual canonically normalized kinetic term. And then the only place where R will stay is in the dimension full coupling. So it will multiply this V square, R square over R prime square. So it will only be in this part here. Remember that the Higgs potential in the initial formulation, which is this part over here, has two input parameters, lambda, the quartic coupling, and V. V is, it's an input parameter of the theory, and it's a mass scale, okay? The natural expectation for the V parameter is that it's of order n Planck. This is really what we know from the hierarchy problem. The mass parameter for the scalar field wants to be close to the highest scale, to the cutoff of your theory. Simply the loops which involve the states at the cutoff will generate radiatively this term. So naturally, you would expect this term to be of that order. However, V is just some parameter in your Lagrangian. This is not the electroweak scale. In fact, the electroweak scale now is V times R over R prime. So from here. Now, if we plug in the natural expectation for V, which is m Planck, then we get that electroweak scale is m Planck times the ratio of R over R prime. Okay? So if this ratio is 10 to minus 16, then this does the job, basically. If you have this large ratio between R and R prime of the order of 10 to minus 16, sorry, the small ratio R over R prime is 10 to minus 16, you will get then the electroweak scale. It also turns out that this is very important. This is what makes Randall-Sundrum model to be on a better ground than, for example, large extra dimensions, is that it Goldberger-Wise mechanism, which serves to stabilize the distance between the scales. It is consistent with having such hierarchical ratio of R and R prime. The way this mechanism works is consistent to having this huge hierarchy between R and R prime. Okay, that is how it works. So let me summarize what I said so far. The fundamental quantum gravity scale is the Planck scale in the Randall-Sundrum model. The size of the extra dimension is inverse TeV. R prime is the inverse TeV. So extra dimension is actually very, very small. We won't have any problems with the tests of gravity. Okay. We do expect Kaluza-Klain modes around the TeV scale, though. The weak scale is actually warped down by this geometry. So we have this warping. We have the Kaluza-Klain states at the TeV scale where the standard model breaks. So the cutoff for the loops to the Higgs mass is warped down to the TeV scale. There will be a cutoff of the standard model, which is very close to the it will be these Kaluza-Klain modes that they will be the cutoff of the standard model. Okay, and if any questions, please stop me and ask. Now, what does this really mean? This so that the weak scale is warped down by the geometry. So this has a very nice holographic interpretation. This goes back to the so-called ADS-CFT correspondence. So the ADS-CFT correspondence is about duality of higher dimensional gravitational theories, weakly coupled theories, with the strongly coupled conformal field theories on the boundaries. So these theories are dual. So this was formally proved for one specific example of ADS5 and N equal 4 super Young-Mills. What does this mean? So in the higher dimensional space, in the bulk, you have this this theory, and then on the boundaries of it, you have some kind of it's dual. Okay, this conformal field theory. So in this specific example, we think of this UV brane to be some four-dimensional conformal field theory. Notice that so it has some four-dimensional CFT on it, and notice this metric here, which is scale invariant. Okay, if we have this transformation, if we multiply z by alpha and also x by alpha, there is this scale invariance, this conformality. And this is broken by branes, the fact that we have a UV brane and IR brane, the fact that we have only the slice of the de Sitter space. But there is this very nice geometrical interpretation. So when you move along the extra dimension, when you enlarge Z, then you are sort of zooming out in your slice. For each Z, you see that you are zooming out because of this warp factor. So in fact, you are going from, you are doing a renormalization flow. So UV is a very high energy, and then when you go along Z, then you are doing in this scale mu. You are doing a renormalization group flow. So what actually happens in this 4D dual picture is that you have this nearly conformal field theory. There is the renormalization flow, and then around the infrared brane, somewhere up, you have the confinement. So you know there will be the dimensional transmutation, and we have already seen this thing. We discussed this thing last time. So the dimensional transmutation, it's how QCD generates the mass scale. So basically, the KK resonances in RS are the bound states of strong dynamics. So in fact, this RS is just the dual picture of for example, these gauge Higgs unification models, the class of RS models, they are the composite Higgs. And this is very nice because now we have a weakly coupled theory where we can, for example, Higgs, we have a calculable potential for the composite Higgs. Okay. So the RS has a 4D dual picture, which is a strongly coupled theory that confines and dynamically generates the infrared scale. Any questions?
Yes, if I may. Sorry,
yes,
unfortunately I missed the first lecture, but if I understand it correctly, the hierarchy problem is solved by making this extra dimension very small. Is that the correct reasoning?
Well, the extra dimension is small, but it has a very special geometry, this warped geometry. So the Planck scale gets, so the weak scale is warped down by this additional warp. So the warp factor A is R over R prime. So the geometry makes the Planck scale warp. The weak scale is warped down from the Planck scale.
Okay, but doesn't that just shift the fine-tuning problem from the Lagrangian parameter to this extra dimension?
Exactly, and this is solved by this Goldberger-Wise mechanism.
Okay,
it's a mechanism which makes this R over R prime natural, the ratio of these to be 10 to minus 16. Well, here with this ADS-CFT correspondence, I wanted to convey the message that this has a dual picture. This 5D setup has a dual picture in 4 dimensions. And basically, what's happening is this dimensional transmutation. It is the way how QCD generates the scale. So you have the running of some couplings from in a conformal field, so in a field theory, a gauge theory. You have the running of some coupling from very high energies, and when you go down in energy, the coupling grows, and at some point there is confinement. And the confinement generates the scale, like lambda QCD, and the lambda QCD has all these tower of resonances. These bound states of strong dynamics are KK resonances. For example, the Higgs, which is localized at the infrared brane, is a composite particle. It's a bound state of this new strong dynamics from a 4D picture. And these gauge Higgs unification models are actually calculable composite Higgs models. The best formulations of composite Higgs, I think, are in these gauge Higgs unification RS models. Okay. All right. So in the simplest RS, in the first RS setup, RS1, only gravity would propagate through the bulk, and the Higgs was localized on the infrared brane, but the other fields were also localized on the brane, other standard model fields. However, this in general is not needed to solve the hierarchy problem. So for hierarchy, you only need to localize the Higgs on the IR brane. Okay, so the Higgs should be here. But in fact, other standard model fields can have profiles over this extra dimension. And this, if you start to entertain the possibility that, for example, fermion, quark, and lepton fields have a profile, then you can actually solve the flavor puzzle. The way it works is that when you match the coupling, the four-dimensional Yukawa coupling, we know very well, is hierarchical for quark masses. The five-dimensional coupling, you can take them to be order 1, some generic couplings in the fundamental Lagrangian. And then you have to integrate over the extra dimension, right? But when you integrate over the extra dimension, you have these profiles of the fields. The wave function of the fields in the extra dimension. You can have hierarchical suppressions in this integral. For example, imagine the light fermions, they are localized on the UV brane, while the Higgs is localized on the IR brane. So this integral will be small, hierarchically small. On the contrast, you have the top right, for example, and somewhat bottom to some extent, which are localized on the infrared brane. So they have large overlap with the Higgs field, and there will be the Yukawa interaction when you calculate integral will be, top Yukawa will be big. So the hierarchy of the Yukawa interactions comes from the overlap of the wave function in the extra dimension. Okay.
Sorry, I didn't quite get that. The flavor puzzle is why there is this mass hierarchy between the different generations, right?
Yes, exactly.
How is that solved by this overlap?
So different generations have a different wave function in the extra dimension. They are localized at different place. For example, the light fermions, their wave function is localized on the UV brane, okay? So they have something like falling profile, while the Higgs is localized on the infrared brane. The overlap between the two is small.
Yes.
So you have something like this, and you are calculating the integral between when you have this product.
But what makes what is responsible for the different form of the wave functions of the different generations? Okay,
so this is assumptions. Okay. So that is what makes an up quark.
Okay, but that somehow seems natural in that model. that
Yes,
those
yes. So
different...
it seems natural to say that some guys are localized at one place and the other one at the other place. So the third generation is more on the infrared brane, and the light generations are more close to the UV brane. So these branes are sort of attractors, which say, yeah. Of course, it's a choice. You are making a choice, but this choice is what defines light versus heavy. All right?
Yeah, thank you.
Any more questions? All right. So now I will just summarize all the landscape of these extra-dimensional models. So the extra-dimensional models, they are first divided in whether you have a flat space or curved space. So if the curvature of the space is negligible, then you have these large extra-dimensional models, ADD type models, where so in flat space, and you have, for example, gravity in the bulk. So some fields are in the bulk. And you have these models, which I didn't talk about, which are universal extra dimensions, where all the fields in the bulk. And here you can see different predictions of these models. For example, ADD says that there is the very large extra dimension is accessible only to gravity. We know that we need to have well, at least three to satisfy the gravity constraints. We needed to have at least 3 or more extra dimensions. And then there is this interesting prediction of black holes at colliders. The fundamental scale is at the TeV scale, where we expect the quantum gravity. The second class of these extra dimensional theories are the ones where we have a significant curvature, when we have a very curved space-time. In particular, that is warped extra dimension. And the first model was RS1, where we have gravity in the bulk propagating, and the rest of the fields are on the brane. So the predictions of these RS1 are spin-2 Kaluza-Klain resonances, narrow spin-2 Kaluza-Klain resonances. Then we can relax this assumption, because to solve the Higgs hierarchy problem, we need the Higgs to be localized on the infrared brane, but perhaps other fields, fermions, can have some profile, okay? They could leak. For example, if they are more on the UV brane, they could leak into the, etc. For example, right-handed top was more localized on the infrared brane. And now there is the whole class of these new warped models where you allow for many bulk fields. So we have this field localization, which can help us to solve the flavor puzzle. Again, the predictions here is that we have the KK resonances at the TeV scale. Now we have not only the KK resonances of the gravity, but since other fields are in the bulk, there are other the KK resonances of other things that could be looked for. For example, in that context, the interesting ones are, for example, the KK modes of the gluon field. Okay. So the interesting class of models are these gauge Higgs unification models. So gauge Higgs unification models. This interesting class of this new warped model building, which then is directly connected to the 4-dimensional composite Higgs models. They are dual to 4-dimensional composite Higgs models. Okay. That's all what I have to say. Any questions?
So Admir, I would have a question now. So these models that require a significant curvature, aren't they already, I don't know how should I say, but maybe excluded because from, I don't know, cosmological observations that the universe is flat, or?
We have this warped extra dimension, which is small. But in fact, if I go back to the metric, which is over here, the 4-dimensional metric is flat. Okay, So the 4-dimensional part is flat. And you can have, for example, we know that we don't live in anti-de Sitter, but in de Sitter space, you can achieve de Sitter in 4D. Some small positive cosmological constant.
Okay.
So that thing about cosmology has to do with the cosmology at later stages when we measure the, for example, BBNC and BS and so on, has to do with the geometry of the 4D space, right?
Oh, okay.
And this is the warping of the extra dimension.
All right. Thank you.
Thanks. That is actually a very important point. In any case, if there are no any further questions, I would stop here.